Hello everyone and welcome to this talk. First of all, I would like to thank the committee for organizing this session and allowing me to participate. My name is Anders Jarmund and I'm a third-year medical student at the Norwegian University of Science and Technology with a master's degree in applied physics and mathematics. Today I will talk about the cerebral hemodynamics in the neonate and describe what we have found relating to how the cerebral blood flow is maintained during mild hemodynamic stress in healthy-term neonates. The talk is based on the manuscript now ready for submission. So this is the question I want all of you to have in the back of your minds during the presentation, as it summarizes our aim. I will start by talking about the tilt, because it is very illustrative for why we have done this study, and briefly introduce cerebral autoregulation. I assume that you're all familiar with ultrasound techniques in general, but I will show you the specific ultrasound system that we have used, as it is quite recently developed, and this study was in part conducted to demonstrate some of the applicabilities of the system. I will also take you through the experimental setup and data analysis, and finally show you some results. Here you can see a neonate laying on its back in supine position, with a heart and a brain in approximately the same height. If the neonate is tilted head up, for example when its mother holds it towards the chest, we introduce a height difference between the heart and the brain, resulting in a hydrostatic pressure that must be overcome. For comparison, the mean arterial blood pressure in term neonates is about 40 millimeters of mercury. So we get this gradient that would make the blood leave from the brain and being pulled into the feet. Luckily, we have several mechanisms that counteract this and ensure a stable blood perfusion of all organs. But today we will only focus on one single mechanism, the cerebral autoregulation. In general, cerebral autoregulation is about ensuring stable brain perfusion despite fluctuating blood pressure. There is a physiological range where the vessel radius decreases as the systemic blood pressure increases, and the blood flow is kept relatively stable. But outside this range, the vessel radius passively changes with pressure, and these ranges are different from individual to individual, making it hard to use only systemic blood pressure to assess the risk of malperfusion, although it's the best we have at the moment. Being newborn is stressful, and some neonates, and especially those born prematurely, can have a less developed autoregulation, rendering them vulnerable to malperfusion, either hyper or hypoperfusion, that may result in brain damage. There are some strategies for managing malperfusion, and it's important to detect it early to begin prophylactic treatment to avoid neurological complications. Now I will introduce NeoDoppler, which is the ultrasound system we used in this study. It was recently developed by Professor Hans Torp and his group and has been tested in different hospitals in Norway. I will show you a short animation. In brief, we attach a Doppler transducer operating at 7.8 GHz to the fontanella of the neonate, and insulate the vessel below. We are able to simultaneously monitor all vessels between 3 to 35 mm from the probe, and we pick the vessels of interest afterwards. The system is designed for continuous monitoring of neonates. So to summarize, we're actually looking at two questions. How does the cerebral blood flow in neonates change during and after a head-up tilt? And if NeoDoppler was able to measure these changes. We have already looked at the tilt test and how it affects the infant and the NeoDoppler system. Now I will first take you through the test setup and then talk a bit about our analysis. We had 44 neonates participating on 2 consecutive days after birth, and we analyzed 56 recordings in total. Here you can see the mean velocity recording from a single test. The infant was laid on his back with the NeoDoppler probe attached. After 40 seconds, we tilted him upwards and kept him in upright position for 200 seconds, before we laid it back again and monitored for 60 seconds, so 5 minutes in total. We measured the blood pressure before start and after 120 seconds as indicated. We divided the signal into 4 time segments, or time windows of 40 seconds. For each of these segments, we calculated the average mean velocity, heart rate, and pulsatility index. Please have these segments in mind as we will return to them later. The Doppler spectrum is automatically traced by the NeoDoppler system. and numbers for mean blood flow velocity, pulsatility index, and heart rate are extracted continuously. So we get these data as time signals, and we calculated the average over the 4 segments as I mentioned. But we'll lose a lot of information by just extracting mean values from a period and ignoring the instant time changes. So to characterize the immediate response, we defined another time window containing the tilt, and analyzed the signal as a time series using k-means clustering for longitudinal data. This method allowed us to identify similar signals. Based on several quality criteria, we chose 5 clusters. Here you can see them. The black lines are the cluster means. The signals were normalized to baseline, that is the mean over the first time segment, prior to tilt. Next, we used linear mixed models to look at how these clusters of immediate responses were related to changes on longer periods of time by using the 4 time segments we discussed earlier. Here you can see how the mean blood flow velocity, pulsatility index, and heart rate change from baseline, that is prior to tilt, and during the test. You can see that some of the differences persist through the test. We couldn't find any predictors of cluster assignment, and the neonate often changed cluster from day to day, but that's in line with earlier research. If you look carefully, you can see that the clusters behave differently and have a kind of signature. For example, if you look at cluster C, it is the only cluster with a decrease in blood flow velocity and increase in both pulsatility index and heart rate. In other words, we cannot distinguish the responses with a single feature alone, but only when looking at several at once. To summarize, we found that healthy neonates present with a range of normal responses to tilt, and with NeoDoppler we were able to detect rapid changes in blood flow velocity. Thank you for listening.